Welcome to the Groundwater Foundation's Educator Toolkit training video on an application exercise for the Hydrogeology Challenge. This video covers the Applied Knowledge Scenario, an optional extension activity to the Hydrogeology Challenge. The rest of the videos in this series are listed here and can be found on the Groundwater Foundation's website, www.groundwater.org. The Hydrogeology Challenge is a basic groundwater modeling tool that's designed to replicate some of the common calculations hydrogeologists make to understand groundwater flow in an area. The next step that scientists face is the application of the model to a problem they're trying to solve. Using results from specific well combinations in the Hydrogeology Challenge, the Groundwater Foundation has developed some simple applied knowledge scenarios. Applied knowledge scenarios allow students to be the scientists while they work through a basic groundwater problem. Scenarios can ask questions about time of travel, risks to future wells, flow direction of a contaminant plume, and even how certain types of remediation might be effective against a given contaminant. Pre-developed applied knowledge scenarios are available by request and are associated with particular well combinations from the hydrogeology test challenges. The scenarios provided by the Groundwater Foundation are a good starting place and can be extended with student-led research. You can also design your own applied knowledge scenario addressing a local or regional groundwater issue that is of interest to your students. Previous educators have used the challenge and scenario as an introduction to complex groundwater concepts, good research habits, and argument construction, usually through the lens of a local concern like a pipeline leak or placement of a feedlot. Creating a unique applied knowledge scenario for your classroom is easy with 6 steps. 1. Identify a well within the map that will be the source of contamination. In the online version, this is best accomplished by choosing one of the wells that was used to calculate the final horizontal velocity. 2. Identify at least 2 wells to turn on pumping. Ideally, at least one of these wells is near enough to a contaminant source to significantly influence the horizontal velocity and flow direction calculated from the map. The contaminated well can also have its pumping activated. For results that are more representative of reality, qualitatively assess the change in flow direction given the new pumping wells, but continue to use experimentally determined gradient and velocity from the map. For experimentally precise results, run the model again using the point of contamination and at least one of the wells closest to the contaminated well that also has pumping turned on. 3. Identify all wells that are now threatened by the contaminant plume, given the adjusted direction. 4. Set tasks for your students to solve. This may include discovering how long it will take the plume to reach the nearest well in danger of contamination, or how long it will take the plume to reach the farthest well in danger of contamination, or how the plume and other wells will be affected if pumping is turned on or off at a given well. 5. Identify a type of contamination or a specific contaminant. Local topics or hot-button national issues can provide a jumping-off point for talking about different kinds of contamination, as well as methods of remediation that are deployed to address it. 6. Set tasks for your students to investigate a contaminant or local concern and the remediation techniques. These may include investigations into the definition, type and qualities of remediation, chemical, physical, thermal, EPA or state regulations, cost analysis of remediation techniques, assessment and recommendations for next steps to remediate the contaminant, and also assessment and recommendations for community leaders to take preventative measures against future contamination. Designing your own applied knowledge scenario gives students a chance to engage with current and local issues in the context of what they are already expected to learn. The added complexity of this kind of applied knowledge scenario to the Hydrogeology Challenge works towards establishing a solid foundation for research and argument construction. The Hydrogeology Challenge allows students to evaluate groundwater flow and predict the impact of human activities on groundwater. It encourages engagement in complex, real-world groundwater problems and asks students to develop evidence-based arguments for possible solutions. Because of that, it's directly aligned to the NGSS requirements for HS-ESS3-4, HS-ETS1-3, and HS-ETS1-4. The Groundwater Foundation also has the current alignment to the Nebraska Career and College Ready Standards for Science and will continue to work towards aligning the Hydrogeology Challenge with unique science standards in other states. Check groundwater.org for updates. Remember, you can view the educator toolkits, including the applied knowledge scenario, on the Groundwater Foundation's website by finding the Student and Educators tab and clicking Educator Toolkits.